Our first English session today.
Cool. Thank you.
So today we have Dominic, who is a CTO from Diode, an IoT company. And he's going to talk about why blockchain is a solution to IoT security. So let's give him a big applause.
Thank you. Thank you, June. Yeah, there's a company here, Exercise, that I'm working for, and we have launched this project. And I want to dive really quickly into this. So the name is a bit provocant. And there's maybe a second name for this talk, which is doing blockchain with Elixir, the good, the bad, the ugly. And we're going to talk about that as well a little bit, because everything we do a lot with Elixir. Thanks for the introduction. I just did a little bit of a summary here. So I actually have lived in Taiwan for 7 years. Now I'm back to Berlin, and we're working from there. In international, there's like a lot of Ethereum going on in Berlin. And we were going to talk about the next item, the block quick algorithm. And we're also active in the Ethereum Magicians. I don't know if anybody knows the Ethereum Magicians. It's an improvement group to improve the Ethereum protocol and to make suggestions. And that's where we do. And what I mostly hack in is, I started with PHP long time ago, and C++ and Erlang and Elixir now is my new stuff. If you hear anybody talk blockchain and IoT, this should be your first reaction usually. Like, whoa, like take a minute. Like, why would anybody have the idea of using blockchain and IoT? So if you hear that, take a little bit distance, and we want to do that, take a little distance and see like what's happening here. So typical IoT devices we're talking about that we do, like in the company I'm from, is like smoke detectors or smart locks. So these are usually very small chips. So like an ESP32 is, even if you know Arduino, like on that level of computational power usually. Like very small machines that we work with in IoT. And getting their blockchain running is not a trivial task. But there's really big security, like some really big security problems that people don't talk about a lot. And this unfortunately is really not readable, but I wanted to highlight there's some like pseudocode here on the left-hand side, and what we thought of this would be better on the right-hand side, and I want to go through that a bit. So when you imagine the store lock, and you buy it at Jalifu, for example, it was offline, had no power, and you were powering it on for the first time. It has to do a couple of things. First, it has to find out what's the current time actually. In an IoT device that connects, how does it find out the current time? It asks some stuff, like something like this. Does a DNS lookup give me the DNS name of my time server? Maybe it does NTP. But like a DNS lookup is already unsafe, as you guys might know. Like DNS is not an encrypted protocol. You just go to some public server, you ask it what's the name, and it gives you some IP address. If the Wi-Fi you're connected to is taken over by somebody, or somebody's in your Wi-Fi network who has bad intentions, he can send you wrong data. There's no verification. The next thing is, it tries to actually ask the server, like what is the current time when you use NTP protocol? That's also not encrypted, not secured in any way. So it's a second leg where you have no security. Then third is, try to actually connect to your central server. Let's assume this is a door lock, or in this case it's a plant control for an energy plant. You try to connect to that, and you again need to do a DNS lookup here. It's again unsafe. You don't know what IP comes back. And then what usually happens here in the last step is you now have an SSL certificate, and you use the current time to check this certificate. The current time you got up here, unfortunately unsafe, because this IoT device doesn't otherwise know the time. And you check it against this DNS name, which you also don't know whether it points to the right IP address. So all of these steps are currently insecure. The main problem down here is, if you don't know the current time, or the current time is probably modified by somebody, by a third party modified, then you can't actually really validate the certificate down here. And if you can't do that, and now your lock of your door, your smart lock, connects to the wrong server, imagine what's happening then. Somebody can take it over, give you wrong data, and so on. And when we thought about blockchain, this is what we wanted to wanted to change is like blockchain is actually allowing us to do all of this securely. And the first entrance point is actually up here at the time. So if you are able to connect to a blockchain securely, like establish what is the most recent block, for example, let's say Ethereum, I get the most recent block of Ethereum in some way, I can get a rough time already from that. And if I have the rough time, I can actually also get from the most recent block, even better, the real server address, the real certificate hash that I need to connect to. And then I can connect to it securely. I'm sorry for like this being unreadable. You'll probably get a copy of this. So this is where we started out. Because right now, if you use any IoT devices, like we just talked about, they probably have all these problems on the left-hand side. So this was like the initial thoughts of what we had, how this could look like. So we get a blockchain like Ethereum, so everything we do we base on Ethereum. We put like a very simple contract on that. A fleet contract, we coined it in the initial proof of concept. It has an address. The device can check the address and then fetch data from this contract. And every time when it fetches data from this contract, it can do a Merkle proof to show that this data is actually true. And if it does that, there's no trusted third party. Right? It doesn't need to trust the server it connects to. It doesn't need to trust any big authority somewhere. The only thing it needs to know is what's the hash of the block, and everything else it can prove. And this is really what we call trustless here. So it becomes trustless IoT. You don't need to trust a third party. You don't need to trust anybody else. I need to be a bit quicker because I have too many slides, so I'm going to try to accelerate. Related to this and this insecurity that's happening is like, you probably saw that in the media, China and Huawei, these routers, like the US doesn't like Huawei routers anymore, and from time to time, China is redirecting traffic. And I wanted to highlight that. This is happening since 2010, and it's happening because the way the internet protocol works, BGP, the Border Gateway Protocol, is actually also not a secured encrypted protocol, but it totally 100% depends on cooperation. So this is one example that Oracle has digged out from 2017. Somebody wanted to send a TCP packet, like an HTTP connection, from Los Angeles to Washington, right? So you should think the connection goes here. But over here, the router announced, I have the shortest route. I have the shortest route. The shortest route for you to go from Los Angeles to Washington is to send it to Beijing, and then to Shenzhen, and then back again to Washington. So all this network traffic went this route. Now, people say like, well, it's HTTPS. There's public key infrastructure, so it's secure. HTTPS is secure, it's encrypted, so nobody can go in, right? Well, if you start out with wrong assumptions, bad things can happen. This is what I wanted to highlight here, and especially the handshake in PKI is right now very problematic. Just to recap a little bit, if you connect securely, like to Google.com, for example, there's like this green symbol, and this is from a certificate. And if you go into your Firefox browser, you go into the details, and you check the security, what you will find, and then go into the details, is that there's a hierarchy. So there's a global root certificate that has signed off Google, that has signed off this web server. And this happens for every website in the world. And for every website in the world, there is a root signature, so global sign. I guess everybody in the room here knows Google, right? The company. Who knows the company Global Sign? And who trusts the company Global Sign? Well, lucky is like some Google trusts it for some reason. Mozilla trusts it. That's why they are global root. But there's a couple of these companies, and most of them you won't know. In fact, there's right now over 3,000 intermediate certificates, so that is on this level, and they can create certificates for any domain on the planet. What this means concretely is that they can do man-in-the-middle attacks. So what's happening here is you get, this is you sending maybe from Los Angeles a packet, and you want to connect to Washington, yeah, or to Facebook.com, wherever. And now your traffic gets, for some reasons, through this middle box. It might be in China, might be somewhere else. This middle box has another root or an intermediate certificate. So what it does is, it gets you at HTTP's handshake, it looks at that, and looks, oh, you want to connect to this guy over here. I'm going to create a fake certificate. A fake certificate that I sign with my root immediately. And this fake certificate I send back to you and say, ah, everything is fine, this is a real one. Then you start sending data, and every time you send data to me, I decrypt the data here. And I read it, and then I re-encrypt it, and I send it over here to Facebook. Now I can read all your HTTPS traffic. And the coolest thing is about that, your browser is going to show you a green bar. It's going to be green. Now, you could say like, well, nobody's doing that, right? The problem is people are doing that. So if you today connect to Facebook from Kazakhstan, and you go through these details, what you will see is that in Kazakhstan, you get this certificate. In the rest of the world, you get this certificate. They all look mostly the same. There's a little difference here. So the authority that has created the certificate is actually DigiCert, so it's one of the big companies like GlobalSign. DigiCert is another one. If you connect from Kazakhstan, it will say Security Certificate is the company. Well, who's Security Certificate? And the country of this company is KZ, Kazakhstan. So it's actually the Kazakhstan government has introduced a global root certificate that you have to install on every machine in Kazakhstan. So they can read all the traffic if you're in Kazakhstan. And they do this because they're not in this list. So this list, I collected that. There's some really good open material from Consensus showing like all the states that have intermediate certificates. So there's right now, there's 3,600, 3,400, 3,800. There's actually a number going up. And so in Europe, you have like 2,000 of these root certificates. A lot of universities, for example, have them. So any university can create, like those certificates that can create any domain certificate. United States obviously has a lot, and you see like a lot of Western countries. Taiwan has a lot, in fact, have it, but it's not all countries. And the question is like, isn't this unfair? Why can some countries create signatures for domains, but other countries not? Maybe. And this is what we wanted to change. We wanted actually to change this in like, let's remove these roots. Let's just not have them. Like, why do we need this third-party global sign to connect our IoT devices? Why introduce this? This is a systematic issue. So this is the trust model we have today. So you have the root store in Firefox. There's 50 roots. They have around 3,000 intermediates. And this is what the root of trust is. And you don't know these companies. You can check them out. You find it publicly with a list, but you don't know them. And you have no idea who these are. But they sign off all your secure connections. The idea here with blockchain is if you are Facebook.com or you are like this company doing the smart locks, you put your certificates into the blockchain, right? You register them here. And the consumer, the device or the user is checking them also from the blockchain. So we gather the blockchain as a central registry for all these secure certificates. And this removes the need to have a third party that can then do funny stuff like Kazakhstan can create this intermediate certificates or anything like this. It totally removes that possibility and makes this communication secure. So why has nobody else done that? That sounds great, right? Like it's like, cool, let's do it. There's something not a lot of people talk about here, and this is, on one hand, how much storage and resources we have on our hardware, and how much we need to actually do fun stuff with the blockchain. So the devices we work with, I said, is like Arduino, like an ESP32, for example, is like a very common Wi-Fi chip from China. If you have like Wi-Fi light switches, Wi-Fi monitors or locks, anything like this, you will probably have a chip like this. And Linkit, for example, is an ARM-based one from MediaTek. They have like 500 kilobytes of RAM or 300 kilobytes of RAM, and storage is like a couple of megabytes. If you look right now into the current client, so you see that you need like 100 times more of the resources. I put like Geth are two Ethereum clients, like it's a standard Ethereum client, has a simple, fast, and light zip. I just wanted to show that because that's like the starting base fast. I'm often getting asked like, why don't you guys use Iota? Like, we tried Iota, and the problem with Iota is it's like Java based and needs like 4 to 8 gigabytes of RAM, but we have like 300 kilobytes of RAM. Like we cannot even start Java on this. Same with the storage. So it's, if you, I guess for IOTA to like give them some credit, if you have an Audi or a BMW and this is your IoT device, I'm sure they can have a real computer inside and run it there. But if your IoT device is small like this, it's not possible. So this is a challenge we started out with. We created this this paper and published that, a new algorithm called BlockQuick that actually is solving this. It's called a superlight client. There's right now 2 algorithms to produce a superlight client that does blockchain validation on very, very little amount of memory. So this is the new addition here. So BlockQuick can also validate Ethereum or Bitcoin, and it's like the storage is 20 kilobyte RAMs, around 50 kilobyte, and this is like what we went out with the paper and then started implementing, and still working on. So what the step like that we started out using is we do everything based on Ethereum because basically we believe what they do is the right thing, and added on that BlockQuick. So BlockQuick just requires a couple of block header changes. So we had to do this, but it's also a new client protocol. So to implement that client protocol, also needs to change the chain, needs to change a little bit. We need more information in the header, and the client obviously needs to implement it more. Also, we're working a lot with ENS, which is the Ethereum naming system. And if you remember in the beginning of the talk, I talked about unsecured DNS lookups, because ENS is exactly addressing that. Because for DNS, the same is true that is true for BGP, that is true for PKI. If you put the stuff into the blockchain and make the blockchain the authority, you don't have the problem with a third party that can just sign off anything. And P2P transmissions. So if you go there, we actually want to be able to connect devices. So we are all about IoT devices. We want to enable devices not only connect and securely check the certificates, but use a blockchain to actually have secure transmission anywhere. And now we go a bit into coding. Like there was a question for us, like how much code do I need to read if I want to understand Ethereum? So we checked out the different code bases, and there's actually Ethereum is cool because it has multiple implementations. I just mentioned 3 here. There's actually more than that. So there's a Rust code base that is pretty nice. And this is clocked, which I used it to count the code in master. It's like 145,000. Interesting added, which is written in C++, is just 90,000. And then if you use Go, or if you look at the Go code, it has like it's like the biggest by far. It's 600,000 lines of Go code. If you take everything into account, they're nearly approaching 1 million lines of code. So far as we wanted to start a branch of Ethereum and implement the pure like BlockQuick and try out and show that the algorithm can work. And the problem with like the very big source code basis for us was that this is also a moving target, as in moving to Ethereum 2.0. I don't know if you guys have heard of that. They're very focused on these changes, so they're making a lot of changes very quickly. And if you try to stay on top of that, you probably have more work rebasing than anything else. So we start with an Elixir prototype. And I mentioned the good, the bad, the ugly. The good part, if you start with Elixir, is there's actually some community and there's some Ethereum work happening in Elixir. So there's an EVM that we use from Eternity. That's also like a Ethereum startup using the EVM. It's open source. There is like a really good network browser, Block Scout. You can browse like your transactions, all of that. We also use that. And you can also obviously use the cryptographic functions to actually do the stuff that Ethereum does. And there's even like a relatively recent full node implementation called Mana that is relatively active. And this is a bit of a software overview here. So what has happened is we have a Diode node, so that's like the blockchain node. We use the compatible EVM, that's what we took from Eternity. You run a new protocol. So this is actually the BlockQuick protocol to talk to these devices. So it's using that algorithm. So it's a new Edge protocol. We do the same Ethereum RPC that is standard Ethereum, so you can use any of the tools like Remix or anything you want. And we also have a new node-to-node protocol. And this is because we want to publish more information about these devices through the whole blockchain network. Most of that is, some of that is level 1. So block width is actually a change inside the node code, inside the blockchain itself. Thanks, 5 minutes. And some of that is level 2, and level 2 means it's actually inside what runs inside the EVM, so it's the smart contracts here. So we also set up a smart contract system here, because the question is, if your devices connect, right? This is a pretty fundamental question that you have with any of these devices to blockchain. Why should this server here, why should you open this port, right? If you define a new port for your block pick algorithm, why should you open this as a miner? A miner is mining his blocks, and he's making some money from mining the blocks. So what is his reason to waste resources in talking to some random IoT devices that don't help him mine blocks? Why would he do that? And so there is a need for an incentive. Why it makes sense for him to actually open this port and let devices ask him funny questions like, what is this DNS address, or what is this PKI address, or anything like this. And so we came up with an incentive mechanism that is implemented up here on level 2 mostly. So we have a registry of fleets and devices, and for each fleet, one of those fleet contracts that contain information for the devices to fetch, but also a way to generate incentive for the Diode nodes. And this is really where I want to go a bit. Like if we want to change the security model, we have to fundamentally address all these 3 things. The BGP, the routing, DNS, the domain name system, both are not encrypted, and PKI is encrypted, but it's centralized. All these 3, like basically the 3 fundamentals of the internet, we want to address, and this is what we're doing here. So we have devices, actually both sides are in the same way, clients, and in the middle, the blockchain network that we use for transmission. So the idea is instead of using central servers, which you use blockchain, a device or a client connects to the nearest node it finds and opens like a persistent connection that keeps open. It can be any of those. It's totally trustless, as long as you can validate that the data you get is the right one. A device then stores its location in the chain, so that's why we have a peer-to-peer protocol in the chain that's near. And the client can use that, I'm accelerating here a bit, to locate it, and then create a connection, either a direct connection between client and device, or a proxy connection through the blockchain itself. And so imagine that, like, if you right now, I don't know if anybody of you has done a Raspberry Pi project, but if you do that and you bring on maybe your webcam or some sensor data, the problem is you can't actually show that to your friends and family because that Raspberry Pi is only online in the Wi-Fi. It's not reachable from anywhere on the planet. You always need like a proxy server or a central server. But that central server either introduces cost or introduces security because it's controlled by a third party. With this model, it becomes serverless. Right? So the chain itself becomes your proxy in a trustless way. Some comments here about writing this in Ethereum. It's fun, it's like little code. And it's especially nice to write in for trees. Recursive functions are wonderful to write in Elixir. But at the same time, if you have large trees, actually copying them in a functional language, like every modification is a full copy of a Merkle tree. If that's big, like a gigabyte big Merkle tree, and you have an immutable functional language, you're copying like a gigabyte of memory all the time. So that, on the other hand, the code you can write to modify the tree is super, super small. Like compared to what we looked at right now, we have like 10,000 lines of code, Elixir and Erlang, and all of this Erlang code is actually the EVM that we just used, the Eternity EVM. The baddest, Elixir is not like for fast computation, so don't rewrite cryptographic stuff in Elixir. And I'm saying that because I did, and I found it's pretty slow. You can still check it out. And I'm scrolling to the end. We don't have time for a demo. We're at the end, actually.
Yeah.
So I'm going to skip that and go to the end. Thank you very much for this.
Okay, so right now we are in a Q&A session. So any questions coming forward?
Yeah, any?
It's pretty good. Cool talk. Yeah.
Thank you.
Because I'm actually talking about, hey.
What if someone is wrong information in
what is the wrong information is the question, right? So I think if you register like an address, for example, like you deploy your smart contract, that smart contract address is yours, right? Nobody can register the same address again. If you put garbage at your own location, you can put garbage at your location, but probably nobody cares.
What if I pretend I own Facebook.com and I register the wrong information before Facebook registered the right information?
Well, this is actually all blockchain. So what you use to authenticate is basically your wallet, right? So you have a private key and a public key. And I used Facebook.com as an example, right? But this is actually like a string, a name. What the devices, like the IoT devices, look at are usually like contract addresses or public key, private key addresses. So if you have the public key, you can prove it because you can sign it with your private key. If you don't have the private key to that, it's really hard to prove. Like you cannot, until somebody breaks cryptography, I guess. If that makes sense. ENS has like a really interesting solution. They want to actually use human readable names, like short names. And so they have an auctioning system. So you can say, I want to buy the name Facebook. Yeah. And then somebody can say, I also want to buy it. And then they can do this. And I think this is a really interesting system. For humans, it's super important because we want to have short URLs. For the machines, like IoT devices, it's not so important. We just use the addresses. But for human interaction, we want to use that as well, probably ENS.
So Dominic, you mentioned like this fake CA problem, and I remember Google has this CT certificate transparency.
Yeah.
And they claim to be effective. So could you comment a little bit?
Yeah, it's very. I mean, Google is really like two-sided sword because on one side they support that. On the other side, they don't trust it themselves. So what Google actually does, and so if you create a fake certificate for Google, what they are doing actually, they check in all their browsers. They have preloaded their own server certificates. They know all our servers have these certificates, and they preload them in the browser. Now, if some like Kazakhstan creates a fake Google certificate, the Google browser itself will send a report to Google, and they will find it in the certificate transparency. Now, the certificate transparency works as long as people contributing are submitting this feedback, right? So if you use a Google browser, the Google browser will automatically send this feedback. If you use an IoT device, it will not send any feedback. It will probably not even implement most of the standards correctly. And if you are in the man-in-the-middle attack, there's even no guarantee that you can send anything back. Like, you get this fake certificate, you can only approve, it looks right, I've never seen it before, but the fact that you have never seen it before, it's not guaranteed that you have a pass to send that back. Yeah, certificate transparency is interesting. Like if you use curl, for example, like it doesn't even check revocations, right? It doesn't do certificate transparency. It doesn't do anything like this. So anything that is that machines do right now is really unsecure. Thank you.
Okay. Any questions? Okay, I guess the time's up.
Yeah.
So let's thank Dominic again. Thank you.